Hello, good morning everyone. Okay, we start lecture 20, inverse functions today. As you see, it's lecture 20. Our last lecture will be 24, so we are getting into the real final stretch. Okay, I want you to be just focused, and we are going to finish with the success. Okay. All right, lecture 20, inverse functions. Well, we learned the concept of inverse functions. Just 1 second, please. Yes, however, what is the inverse function? Yes, we have some adjective over here. So I want you to look at these cases. The first one is 1, 2, 3. Okay, the second one is 1, 2. I'm going to do just 1, 2. Okay, A, B, C here and here. And the third one is 1, 2, A, B, C. Here 2 goes over here. Okay. So I'm giving you 3 relations over here. Relations A, relations B, relations C. Which one is a function? Number 1. Okay. Well, you know the function means for each x value there will be only one y value associated. But guess what? This one goes to A and B, so this is not a function. So, what about this? Well, this is a function because for 1, x value 1, it has only one output A, and for x value 2, it has only one output A, but only issue is that 1 goes to A and 2 goes to A also. What about this? This is 1 goes to A and 2 goes to C. So both are functions, but over here we call this one one-to-one function. It's like a monogamy, okay? You have a different input and it means different output. So we call this one-to-one function. Alright? For each x there is one y value, and conversely for each y value there will be only one x value. You see? For each y value here, y value A has 2 corresponding x values. So this is not one-to-one function. Yes, this is a function, but this is not one-to-one. Yeah, one-to-one, it takes too long to write it, so I'm going to do it by OTO for one-to-one. Okay? So today's topic is on one-to-one function, and once the function is one-to-one, and then we can make inverse function. Okay? So, in the top one-to-one function, in a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only 1. So both blanks are for 1. Okay? Another way, a formal way of writing this one-to-one function is that if A and B are different, and then f of A and f of B are different also. Okay, that is another way of saying if this function f is one-to-one. Okay, so let's look at example 1. Decide whether each function is one-to-one. Okay, f of x equals negative 3x plus 7. So let's look at this. Let's pick 2 different x values for anything, okay? So I'm going to choose x equals 1 and x equals 4. See what happens. What is that? F of 1 is negative 3 plus 7, which is 4. And when x equals 4, f of 4 equals negative 12 plus 7, which is negative 5. We started with two different input, okay? 1 and 4, two different input, and we end up with two different output, 4 and negative 15. Well, this is just coincidental, only this case just accidentally it is like that. No, you pick just any two values, they should be, the output should be different because we do the same, we take the same action, and they are going to produce different output. Okay? So this is 1-to-1. And the part B is f of x equals the square root of 49 minus x squared. When you see x squared, you should suspect something because you are going to put x equals 1, for example, x equals negative 1. Two different x values, right? Two different input. And see what happens. F of 1 equals the square root of 49 minus 1, therefore square root of 48. What about x equals negative 1? Well, f of negative 1 equals the square root of 49. Guess what? When you square negative 1, again that is a positive 1. So 49 minus 1. So again, we are going to have same output, even though those inputs are different. Okay, inputs are different, but they have the same output. So this is a case that we say, hey, this is not one-to-one function. Okay, all right. Well, is there any way to see like a graph and then tell this is one-to-one or not? Yes, there is a way. You remember vertical line test? Vertical line test was used to determine each given graph is a graph for function or not. Okay? But today we are going to have horizontal line test, not vertical. Okay. Horizontal line test. This is for one-to-one function graph. Function graph. Okay? So let's see. Earlier, I'm going to show you just, so let's say there is a straight line, and there is, parabola. We studied the parabola, a lot of parabolas the other day. And so let's say this is like up and down like this. Okay. I'm going to make it a little more up and down. Alright. There are three graphs over here. There is only one graph shows one-to-one, which is the first one. Because for each different x values or different inputs, so I'm going to pick here and here. So I'm going to say A and B, they are different, right? So when you go to the graph, this is f of A and this is f of B. They are different, okay? So this horizontal line test means this. You just draw horizontal line just at anywhere, and we say arbitrary horizontal line, and each horizontal line intersect the graph at only one place, or at most one place. Okay? If that is a case, it is a graph of one-to-one function. So I'm going to show you two different ways. Okay, so this function is one-to-one. What about this one? I would say this very obvious points here and here. I'm going to say A and B. As you see, A and B are different. So let's call this function f of x. What about f of A and f of B? Oh, f of A is 0 and f of B also 0. They are equal to 0, both of them. So this is not this way, correct? Okay? So this is not one-to-one, okay? This is one way of just showing that algebraically this is not a one-to-one function graph. On the other hand, graphically, just I'm going to draw a horizontal line over here. This horizontal line intersects the graph at two different points. That shows that this is not a graph of one-to-one function, and that this is how we use horizontal line test. Okay, so this is not one-to-one. And again, let's go directly. Okay. Wow, this line is intersecting the graph at three different points. Well, some places 3, some places 1, okay? This point is like a 2, but it doesn't matter. As long as you see at least one line, okay, just one line that shows the different, intersects the graph at more than one point, that means already it fails the horizontal line test, okay? You don't have to make it too many. Just you show just one line, one horizontal line that intersects the graph at more than one point, that means it fails the horizontal line test. Or you may say over here, this point A, this point B, this point C, they are all different, but they have what? A and the B and the C, they are all different, but f of A, f of B, f of C, they are all the same thing, okay? So this is not one-to-one function graph, okay? So that is the meaning of a horizontal line test. Now you can see example 2 very easy. Example 2, using the horizontal line test. So, example 2, you already know the answer. This, and the other one is parabola upside down. You see? Yeah, it fails. So, it's not one-to-one graph of one-to-one function. On the other hand, this one, wherever you go, yeah, it's going to intersect the graph at only one point. So this is yes, this is a graph of a one-to-one function. Let's describe these graphs a little differently. In this graph, the function is increasing somewhere and then decreasing, right? Increasing and decreasing, therefore it goes through, well, two different points at the same y value. Here is just decreasing all the time, all right? So, or the graph is just increasing all the time. This is a one-to-one function graph. So, just graphically or visually, this is what you can say. The function is going to be only increasing or only decreasing. In that case, the function is one-to-one function, one way or another. Okay? So let's see, either only increasing or only decreasing. If you have a mix of increasing and decreasing, no, that is not the graph of one-to-one function. Okay, I think it's clear by now. The next one is, okay, so in general, so let's see, the one-to-one functions are, so only one way, so one-to-one function examples, so y equals negative x, yeah, the graph is this. Or y equals x cubed. Do you remember the graph? Basic function graphs over here, like this. Or y equals square root of x. Yes, the graph is from here and then going up. So just only decreasing, here only increasing, and here also only increasing. These are the examples of one-to-one function. Okay. And now the inverse function. Okay. The concept is this. Okay, well, nowadays I stay home all the time, correct? Okay, I do not go anywhere. Let's talk about good old days. Yeah, just 1 month before, yeah, we are free to go out and then go somewhere. So let's say this is a home and I went to office at UNF. Okay. Going over here, I would describe this one as a function f. Well, after my work, I go back home, right? So assuming that I do not stop by anywhere else. So I go home directly and exactly the same route. This is a concept of inverse function. So earlier I closed the door because this is our home office and the door was open. Well, so I close the door. After videotaping this, what I'm going to do? I'm going to open the door. So close it, open it. Okay? That is another opposite thing. So that is called, you can say, the concept of inverse function. So you do something and you are going to undo it, undo what you have done. Well, that is a concept of inverse function. Okay? So here, when you do that, the inverse function, yes, it looks funny. Yeah, it looks like a -1 power, but please do not say this is -1 power. We call this inverse function of f. Okay? Inverse function of f. So conceptually, more precisely, now let's go this way. So you have 1, 2, 3, and you have A, B, C, and this. You have a function f is relative, okay, like this. Is this a one-to-one function? Yes. If you have a one-to-one function, and then we can talk about the inverse function. Because when you make an inverse function, already we say this is a function. That means for each input, it's going to be, it has only one output. So when you go here, inverse function means, as I did, just we're going to opposite direction. So I'm going to reverse this arrow over here. And I'm going to reverse this arrow and then reverse this arrow. That is the inverse function. Okay? So I'm going to write it this way. F of 1 is A, f of 2 equals C, f of 3 equals B. Now you go for inverse function, then f inverse of A equals 1, f inverse of B equals 3, you see, 3B, f inverse of C is 2. See, I reverse the arrow direction, and by doing so, I create another function, and we call it inverse function of f, because that one came from in function f anyhow, okay? So this is a concept. So if I write it as a coordinate, this is a 1, comma A. I'm going to use black for all the functions. F, so 1, comma A, 2, comma C, 3, comma B was on the graph. Now when you go to inverse function, it's going to be just what? You switch x and y coordinate. 1, comma, A, comma 1, A, comma 1, 3, comma B. You see, I just swapped x and y, input and output, and B, comma 3, C, comma 2. So it's very simple function. Inverse function means simply you swapped x value and y value, or you may say input and the output. When you look at the coordinate, you switch the x coordinate and the y coordinate. Okay? So this part is inverse function, but you can have an inverse function only when if the function is 1-to-1. It's very important, okay? If function is not 1-to-1, you cannot make inverse function, okay? Again, let me emphasize this. If function is 1 and 2 and A and B, so let's say this is not 1-to-1. When you want to reverse the arrow, yeah, this one goes to here and this one goes to here. So when you have F inverse of A, you have what? 1 or 2. You cannot have this one. Okay? That's why only 1-to-1 functions have inverses. All right. Okay, now we go more technical definition over here. Inverse function. Okay, and so let f be 1-to-1 function. Okay, then it has f has inverse. We call it what? F inverse over here. And the relation we can find over here is you compose these two and then the result is going to be x. So in other words, you start from 1, you are going to have 1. Because what do? You go one direction and you come back. So wherever you start from, you are going to come back. That is the concept of you are applying, compose these two function and its inverse over here. So what about the other way around? Same thing. Okay? You apply f first or apply f inverse first, doesn't matter. The result is going to be same x because you start from A, go to 1, and you are going to come back A. That's why you come back to the same input. Okay? So, example 3. Yeah, I think you had homework problems at the end of this compositional functions. Yes, I think I picked one problem about this. Okay, you compose it and then the result is going to be just x. So example 3. This is a nice case that they already gave you two functions and then you decide whether these two functions are inverses. Okay, so f of x equals 2x plus 5 and g of x equals 1/2 x minus 5. Okay, is g the inverse function of f? Is g the inverse function of f? i.e., is g is f inverse? Yes, you can say just briefly, really in